Pedro, Leisha, Johan, Pedro, Kaylin, Carlos, Catherine, Kaylin, Levy, She, Jason, Jeremiah, Cindy. Alright, you should be pretty much done with these problems by now. Jennifer, Angela, Rhiannon, Michelle, Osi, Omar, Christian, Diana, Samantha, Fatima, Natalie, Emilio, Javier, Edgar, Samantha. Got it. Page 11. Straight in. Alright, y'all. Here we go. Stamps all around for these 1, 2, 3, 4, 5, 6 different answers, means 6 different stamps. We're just really quick identifying what is the leading coefficient, what is the degree, starting with Angela. Degree of this first one. 4. This highest exponent is a 4, so we say it is a degree 4 polynomial. Calling someone for the leading coefficient.
3.
3. The number in front of that is a 3. Carlos, calling someone for the next one.
7. 7 for degree.
7 for the degree. So notice it's not the first one, it's just the biggest, so you gotta look for it. And the leading coefficient, calling someone for that.
Wow.
And the table loyalty over there. -2. So I know it's a 2. I know it's a 2, but we're going to be talking about whether it's negative or positive. So make sure you write down that it was a -2 along with that. Okay, call someone not at your table for the next one. 3. And the leading coefficient, if you don't see it, call in one more person.
Okay, she called me.
Oh, no,
I said 1, right?
Okay, I said 1.
Was it, sorry, I missed all that. Was that Leisha?
Yeah.
Wait.
No, we should be able to handle this.
Alright, it's 3.
Is the degree.
And then 1 is the other one.
Okay, so we're just going to take care of everyone here. So there's no room for debate except for you. And then over here. Cool. Oh, man, Gio gets lucky. Okay, cool. So we got 3 and 1. Happy? Man, stamp madness. Okay. Bring it back on Wednesday. We gotta focus. Wednesday, Pedro, Edgar, I need you like full time with me. Okay. The reason we just did that super quick was because today we're going to be talking very similar to, if you remember when we talked about monomials, how if I identify something as an even positive, that means the degree is even, like here a 4 is even, and the positive is that the leading coefficient, that's a positive 3, right? Even though the 3 is odd, this would be considered an even positive. However, this was for monomials, which was if we had one term, right? Notice these are what we call polynomials because they have multiple terms. So today we're going to see that our graphs are similar to the monomials, and that the end behavior is going to be the same. So if this is an even positive leading coefficient and degree, then the graph might not look exactly like a U, but the ends of the graph are still going to be positive infinity headed up. Just the middle of the graph could be doing all sorts of crazy things in between. Okay? So that's what we're going to be focusing on today, and you'll see right below we have right here kind of the same breakup of odd positive, odd negative, even positive, even negative. And remember, by even or odd, I am referring to which one? The degree or the leading coefficient? Take a look, raise your hand if you can figure out for me. By odd and even, am I talking about the degree or the leading coefficient in front? You can look right here. It says odd or even what? Diana? Degree. So I'm looking at the little exponent for odd or even. For positive or negative, I'm looking at what? Pedro? The leading coefficient. Okay. So let's take a look at the first one. If it is a odd positive, that means for my graph, it's going to look like almost like the cubic where it goes up on this side and down on this side, except it could do any number of things in between. We don't know. So I'm just going to write for right now those like tail ends. I know that it's doing this, going up over here and down over here. Okay? Which means as x goes to infinity, pay close attention, they're not on the right sides. As x goes to infinity, which side is that talking about? The right or the left? That's the right. What's happening on the right? Where are we headed?
Positive.
Infinity. Okay. As x goes to negative infinity, that's the left. Where are we headed?
Negative.
Negative infinity. Okay, that's what's going to happen for odd positive. Let me give you a random example that I just graphed on my calculator. This is odd, the 3, right? And positive, the 4 is positive. So that is an odd positive. When I graphed it, it looked like this, which obviously does not go through the origin like our monomial did, but it still goes down on this side and up on that side, right? So we have that same end behavior. Cool? Okay, next one. Odd, negative. Odd, negative should be the opposite. It should go up over here and down over here. So we would have that it would be negative, positive. I came up with a random example, and my random example was negative 3x to the 5th. That is odd, and it's negative, right? And when I graphed it, it looked like this. So see, this one does actually pass, it looks like through the origin, but what we're more looking at is our end behavior. C is up on the left, down on the right. Cool? Even positive. If it's even positive, anyone remember? Even positive? Up on both sides. And so both of these are going to be positive infinity. I made up an example. 2x to the 4th minus 3x cubed. The only thing that's controlling this is that term right here, right? I don't even care about the other stuff. That's going to affect what happens in between. But this is going to tell me that it's up, up. Let's take a look. See how it's like does all sorts of funky stuff inside, but both of the ends are rated to infinity. Okay? Last one, even negative. Where's it going?
Down.
You probably figured that both of the tails are going to be going down. Here's an example that I graphed, and both are going down. You could make up, I challenge you tonight to make up any polynomial that's even negative, and try to find one that's not down, down. You won't find it. It'll all be like this. Okay? Question? Yeah. If it's a polynomial, it could go through the origin, it could not. We're going to talk towards the end of class about like where it's going to then cross things. Right now, for the first part of class, we're just worried about the ends. Okay? Cool. So what you're going to do right here, rapid fire speed, is look at these polynomials, determine whether it's even positive, even negative, odd positive, or odd negative. Based off of that, I want you to draw your little tails. You can't draw the whole graph, so you're not going to pick up your calculator. You're just going to draw the tails and fill out your limits. Okay? Super quick, with your neighbor. 4 of these. I'm going to give you 3 minutes, because I don't even think it'll take a minute for each one. Okay? 3 minutes. See what you can come up with. Okay, so by even and odd, what am I referring to? At the highest degree. What we didn't do first. Yeah. So is this even or odd? Odd. Okay, so write down odd. And then the number in front is like a 1 if nothing's there. Is that 1 positive or negative? Positive. So this is a positive odd, which means it's going to look odd positive. It's going to go up over here and down over here. Okay. Looks like you're right. Okay, about 30 more seconds, see if you can get to all of them. So this one you would say, yeah, infinity over here. Yep. And this one means that side, yep. So where's it headed? Yep.
Hey guys. With this one, we have to just hardest thing.
Good pictures now, so you can go fill your limits too.
We carry each other.
If this isn't even because of the 4, and it's negative, even negative, both of them are headed where?
Why you gotta be so negative? Oh my god.
No, Carlos is so negative.
Yeah, he's that negative person.
No, you're bringing
Like
it
everybody's
down.
like, oh yeah, we can do this and
You're
that.
not.
Guys, we're gonna put out. Come on, bring it out.
There's a difference between negative and realistic. Gotta be realistic.
Be negative.
Like that.
Also, where do you get positive?
Oh yeah. That's so weird.
That was like, your might. And then
This one should be odd. Right, for the limits too. Because there's an yes that, so you gotta.
What about it? I heard something.
Yes, I hear you.
All right, we're gonna bring it back for the sake of time.
And then look up my.
I am going to show you the entire graph. Obviously, you were just writing like the little tails, right? But I'm going to show you the entire graph so we can also confirm that, okay? So I went ahead and graphed it just so we can see what happens. Notice, we didn't have any idea what was going on the inside, but we should have known that this should have been going up and this should have been going down on this end because it was an odd positive, right? Cool. And so you should have here positive, negative. Cool. For the next one, if I graph it to check it, it looks something like this. So you should have had it up on the left, down on the right, which means you have negative, positive. Ooh, we're slightly short on time. I'm going to run through these last two. Keeping us on track today. Negative, even. I graphed it. It looks like this. We're going to learn later this unit how to figure out all of this stuff, but for now we know. Down on both sides. Negative, negative. Awesome. Anyone got all of them so far? Okay, last one. Even. There's not going to be two positive, right? One of them's even, odd, and one's positive. So let's look first at the exponent. Let's look first at the exponent, even or odd? Even. Now we look at the leading coefficient. Positive or negative? Positive. So even positive. And that would be up, up. Right? And so infinity, infinity. But I think you said positive, positive, but you meant even positive, right? Okay, cool. Alright, so that's how we talk about our end behavior of a graph. So a polynomial now, we should be very clear on what the ends of our graph are doing before we even pick up our calculator. Next, we're going to talk about two other characteristics. How many zeros there could be, and how many turning points. So by zeros, another word for that you're seeing right here is the roots. So let's just clarify really quickly. What am I talking about when I'm saying roots or zeros? What does that mean, roots or zeros? What am I looking for visually on the graph? Raise your hand. You can tell me, Samantha.
Exit or something?
Yeah, where it crosses, if this is my function, I have 1, 2, 3 roots or 3 zeros, right? Okay? So what our task now is to actually this time use your calculator and graph these functions and determine, pause for me, pause. Neil, pause for a second. Determine how many roots and then how many what we call turning points. Let me explain what that is. By turning points, I mean basically relative mins and maxes. Anytime that it goes from going up to going down or going down to going up. So how many turning points would this graph have? 2. That's what you're writing here. Okay? Graph it on your calculator. Record what you get, and we're going to see if we can make some observations about those. Okay? Go. Graph it. See how many zeros you want to figure out what they are. You just Pedro, you got your calculator?
I want to try so bad. I did so bad.
Oh,
I couldn't
okay.
see
So we're
it.
gonna like tomorrow next week. I'm around to get Okay, I need it because whenever we do things like this, like
so bad. I want to
Taylor, you have one? Where is it? Can you get it? Because this is not going to be the only one we graph. So graph it, so you should get. Let me see it. You graph one? Whoa. Cool. So how many times does it cross the x-axis? Looks like 1, 2. So that's your roots, or 2? I don't think anyone else came. How many little, like, tiny little points do you have? Lovely. And if you could draw a rough sketch for me so I can see what you're seeing, that would be wonderful. Oh, darn.
Is it USF Peru?
No, it's
Okay, so how many roots? How many times does it cross the x-axis? Good. 2. How many turning points? That's like little peace of valley. 3. Good.
Do we have to draw it? Yeah, we can.
Just do a little sketch. Good.
Yes. Cool.
Yeah, that second one looks just better than What do we got for the first one? Okay. How many roots then? How many times does it cross the x-axis?
2-0?
No, it's fine.
2. One's right here. One's right here. Right?
The next one too.
So that's 2. Turning points. How many times does it have like a lower and Thanks. Are like any of these high and low as well as sources?
Is the second one 22? 22.
So how many little roots do you have?
You know what looks like? Yeah, 2. No, I said
So we either balance at that point or cross. As long as it touches,
I was watching
the turning points you're talking about are the roots.
right, and I was watching
The root, it touches once over here and then once right here. It just barely touches it, it just doesn't
Is it
cross it,
awkward
but it
to
just like looks it.
watch like, I guess like
That counts.
a
Anytime it
rated art
touches
scene
it.
with your parents and like,
Yes.
it is, right?
It's so
I feel like,
Is it moving over here? It's actually my parents make Alright, I'm gonna give you about 10 more seconds. If you didn't get to all of them, that's okay, but I'm gonna keep moving us forward. So take about 10 more seconds to finish up your conversations.
What do you mean? Something happened?
Alrighty. Voices off, eyes back up here for me. Alright, wonderful. If this is our first graph, roughly when you graph it, you might have seen something like this. So Christian, you're up first. What for turning points in roots? Sorry. Cool. 2 and 3. Everyone else, I should have voices off. I'm going to start giving them to Merritt if we're talking when other people are talking because I got to keep us all together. Christian, calling someone else.
Chris.
Pedro, next one.
I said there's 2 roots and 2.
Okay, so still waiting. For the roots, a couple people asked me. I know this one doesn't cross, it just like bounces and touches. We're going to talk more about what we call that tomorrow, but as long as it touches, we're going to consider that a root. And then for our turning points, I know here it kind of looks fishy of like, is there another little point where it turns? But if you zoom in, it's decreasing the whole time. So there's only these 2 spots that it's turning at. Okay, last one. Call on someone else. Who did I have? Pedro. Call on someone. Natalie. Wow. Who? Gio. What'd you get? Did you graph that one?
Yeah.
What'd you get? 2 roots. And how many turning points? 2 turning points. Cool? Happy? Okay. So waiting, y'all. Okay. So for these, we can identify it from a graph, but the goal is kind of like before. We're hoping that when I give you this equation, I'm hoping now we can come up with some patterns to see how could I figure out these from just looking at this equation. Probably, I'm going to be looking again at, remember this like key information we got, either the degree or the leading coefficient. What we're going to look at is this degree right here, okay? So if you look at the next box, we're going to learn something about how to determine something about the zeros and turning points given n degree, right? Whatever that highest degree is. All right, let's read. For a polynomial function of degree n, it will have at most, this is key, it's not exact, it's just at most, n distinct real zeros or roots, and at most n minus 1 turning points. So let's talk about that. Let's say this is our polynomial, 3x to the 6, blah, 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 blah. Emilio, if this is our function right here, take a look at it. What is your degree? What's your highest exponent? 6. So n equals 6, right? Our degree equals 6. That means, at most, it could have n real distinct zeros. So what is the most possible number of zeros we could have? It's possible that this goes 1, 2, 3, 4, 5, 6, and you have 6 zeros or less. The thing about this rule is that it doesn't help us completely because it doesn't tell us exactly how many. It just tells us 6 is the most. It could be 6, 5, 4, 3, 2, 1. If you graph this, it ends up being only 3, but we know it can't be any more than 6. There was no way it would cross like 7 times or something like that, okay? So that's one thing this information gives us. It also tells us we have n minus 1 turning points. So if our degree was 6, what's 1 less? 5 is the most number of turning points. It could at most turn 1, 2, 3, 4, 5 times. You're not going to see it zigzag any more than that. And here it only ends up like having 3 because it's 5 or less. So this rule is helpful because we see some like interesting stuff about our functions, but at the same time, it doesn't tell us the exact amount, and so it's kind of also limiting. But it's still a rule that we learn in pre-cal and we like need to know. Yep?
So since we have that, are we gonna have to know that specifically, or if that's not gonna help us?
Yeah, like literally y'all could see a problem that says, here's your polynomial. What is, without graphing, non-calculator section, what is the most number of turning points? And you need to know turning points is n minus 1, so you need to say 6 minus 1 is 5. I could say what's the most number of zeros? You would need to know that's exactly n, and you would need to say 6 is your most. Cool? So that's just like a rule we need to know so that we can start to describe graphs even if we don't know exactly what it looks like.
So the degree is 8, the most it can have is 8, but it can have less than 8.
It can have less than 8, yep, and that's for roots. What about turning points if the degree is 8?
Turning points, it's minus 1, so
So
the most it would have 7.
It would have 7. Good. Perfect. All right. So,
Can I get a stamp?
yeah, let's recap one more time. Where did I get this n? Like, what does n represent again? Someone else? Someone with a hand?
What happened?
Yep. It's the highest degree, like the highest exponent. This highest one was 6. So that's why we said n was 6. So our roots was 6 at most. Our turning points was 5 at most. Cool? Alright. So for these problems that we are going to start today, we'll have 6 minutes to work on them today, and then we will continue with this practice tomorrow. Tomorrow is like a continuation of today, except we're going to talk a little bit about like when we bounce, like some people were asking me about. For these problems, I am asking you, if you read these directions, I'm going to summarize for you, for a bunch of different things. You need to find the degree, the leading coefficient, the number of possible real zeros, the number of possible turning points, the end behavior, that's 2 limits, and then At the very end, we also are going to talk about, to kind of close out, how we would actually determine where those zeros are. Not just how many, but where are they. So we're going to come back to that one in a second. I'm going to give you a moment now to take a look at this. Without graphing, don't pick up your calculator. Using the rules we learned, I want you to determine these things. If you want to shorthand on your paper, write like LC for leading coefficient, that's fine to save some time with writing. But I want you to find these 1, 2, 3, 4, 5 pieces of like information about our graph. Go. Find those things, given that equation. Yep.
What do you mean by behavior?
And behavior, that's those limits again. So that's
Oh, okay.
based off of whether it's even positive, even negative, all that stuff, right? So Levy, you over there, I'm gonna make sure you're with me. What's our degree? Let's knock this out quickly. What's your degree?
3.
3. See, just start knocking it out. What's your degree? What's your leading coefficient? 1. Okay, keep going. Write that down. Boom, boom, boom. Yes. Yes. For this, I want you to write not just many, because since they could be different, I need to know which one is on which side. So I literally need to see the entire, I know it's gonna like, but I need you to write the whole thing, okay? So write for me, they were both infinity, right? It's odd. Odd positive, should have been this.
Turning on.
Perfect. Okay. The possible real zeros is the rule we just learned that says it has at most n real zeros. So whatever this degree is, that's n. So the most numbers of times it's going to cross is 3. Cool. For turning points, it's n minus 1. So this is n minus 1 would be 2. The most turning terms it's going to have is 2. Correct? Alright, y'all. Bring it back so I can close at least one example today and we can practice tomorrow. Tomorrow will be like practice day. Eyes up here. 3, 1, 3, 2. And our limit as x goes to negative infinity should be on the negative side down here. It should be going down to negative infinity, right? Odd positive. And the limit as x goes to positive infinity should be going up positive infinity. Okay, so we've got a little more information about our graph. We know it could cross at up to 3 points, right?
Yep.
So now the goal is to actually figure out where are those spots, because then we could get even better at like sketching this without picking up our calculator, because the goal is to try to do this by hand now. In certain cases, you guys already have the skills to do this, and this would be one of those cases. A 0 is literally where this equation is equal to 0. So if this is a quadratic or something like this, you could like do your box, right? However, this is a cubic, so it's a little more challenging. So you're only going to be able to do this until we learn like synthetic division and some tricks. You're only going to be able to do this if I give you some like special cases like this one. Because notice, all of these have what in it? An x. So what we're going to do more of tomorrow is taking out an x. And then we have something that we can do our box with. And we can actually factor this whole thing by hand and figure out the parts that we're going to cross out. Okay? So tomorrow, remind me, because my different classes are in different spots, that this is where we left off, and we will finish factoring. Okay?